So good morning. It's my great pleasure to welcome you back on this Thursday morning. We'll have a session for 1 hour, and it's my great pleasure to introduce the speaker today. We have Professor Peter Zoller, who is a very renowned theoretician. He works on quantum optics. He has made seminal contributions in areas connecting quantum optics to quantum information, realizing condensed matter systems using synthetic quantum systems and so on. So he's going to give us this talk. I remember that the title had something about a quantum leap. So hopefully he'll tell us about it in the next 50 minutes.
Okay, so good morning, everybody, and thank you very much for inviting me here to say that this has been a very exciting week here because I sort of get a cross-section of talks that I normally don't hear. I guess that today is really Quantum Information Day. There will be a whole series of lectures, so I'm the first one here, so I should also maybe give it a little bit of historical aspect. We are celebrating 100 years of quantum mechanics. Heisenberg and Schrödinger, actually physicists seem to like to celebrate because we just celebrated Planck 25 years ago, and now the whole thing again. Of course, this is the real start of quantum mechanics 100 years ago in the theoretical sense. But we're also celebrating, I would say, 30 years of quantum information. 94, 95, the Shor algorithm was written down, and I consider this to be really the starting point where things got serious. And of course, this goes together why we have now the UNESCO year of quantum science, and the word technology is also mentioned here. And of course, quantum information is really going over where basic science becomes a technology. So in this sense, I will talk about quantum information, but I added here in my title here, AMO, because I'm an atomic physicist or a quantum optician, as you might call it. And I'm coming from the group of people that think very much about how to implement things. And we came up with ideas now, starting about 30 years ago, really triggered by the Shor algorithm. And I emphasize that when we talk about quantum information, it's really broader than quantum computing. This is always sort of emphasized quantum computing. We have simulation, communication, metrology. There's this whole world, of course, of quantum algorithm, error correction. All of these things come together. So it's not only quantum computing alone, and I will talk in the following also a lot about quantum simulation. So I will tell you some physics and also some history in this context. And let me start out by simply saying that I sort of put here this birthday of quantum computing, really, and the point, when Peter Shor wrote down in 94, an algorithm, Shor algorithm, and what it showed and why it's so historically important is that it was shown that quantum computing is invented by Deutsch and all of these people, and we have to mention also Feynman earlier, really solves classically hard, but also relevant problems, and they go beyond physics. So this is not solving a physics problem, this is really solving something that normally computers do. They have nothing to do with the electronics engineer that sort of invented them. And I would sort of say at the same time that this is kind of a double birth in the sense that Shor, a year later, came up with the idea of quantum error correction. I guess we would not be here today if quantum error correction did not exist. There will be talks in the following by Bava or so. And it simply says, and this is the connection to physics, that quantum computing can be built from imperfect components. So the combination of these things is, I think, essential. But this was also the time when people started to think seriously how to build quantum computer, and Ignatius Sirac and I at Gila at that time, came up with ideas, and I would like to tell you a little bit about the background of these ideas from the atomic physics point of view, why atomic physics is sort of a great way to implement many of these things from quantum computing to communication and all of that. And the question was how to build a quantum computer. And then I'm going to tell you the story from the atomic, molecular, and optical point of view. In the meantime, of course, we not only have trapped ion quantum computing, this was followed by the neutral atom, Rydberg, that's now very, in everybody's word. Quantum computer, we have photonic quantum computer, and as you can see, I even included here superconducting qubits as honorary members of our AMO community, because I would say the spirit behind, circuit QED, that's really what we did in atomic physics, but what's done in a very ingenious way is sort of to replace the real atoms by artificial atoms. We can argue if this is better. As an AMO person, I have my opinions over here, but in spirit, that's very similar. So this is sort of a package of different platforms, and it's quite interesting to see, they were invented around this time, about here, a few years after this, 94, but they're still propagating today. Okay, and all of them have their own meaning, and I'll comment on the AMO part of that. So, for me, the whole thing started, if I had here a personal note over the conference at Boulder, ICAP. It was actually Dave Wineland who organized it together with Carl Wyman, 2 Nobel Prize winners, a little bit later on. And Otto Eckert was invited to this conference, and he talked about quantum computing, and in particular, the Shor algorithm over here, this paper, bringing it to the atomic physics community. And he asked the question, how does the AMO community know how to build a quantum computer? That would be very relevant. And Ignacio Sirac and myself were in the audience and heard that what we needed was, qubits. We needed single and entangling quantum gates, and the Vincenzo list, of what we need to build a quantum computer. And the essential point, of course, was how to control entanglement. And actually it turned out that AMO, based on the development of atomic clocks that I will tell you now a little bit in the following, had many of these ingredients, not all, already in the lab. So we felt that this was a great opportunity for us, and this was the point where Ignacio Sirac and I, sort of coming out of this talk, noticed that, well, Dave Wineland down the road has this linear ion trap built for atomic clocks, so we can convert these existing setups into something which is a trapped ion quantum computer, which is, from our perspective, like cavity QED with phonons, and which was a way then sort of where these trapped ion platforms kind of developed from this point of view. For me, it was one of these moments that we were working on these systems, not knowing why. We think about generating entanglement, but hearing this talk, it gave us a deeper meaning. Finally, sometimes you have the feeling that I have a very good answer, but what was the question? And here was the question that was given to us. It was, in this sense, quantum computing. So why was, and see this really as a broader context, the AMO community ready for quantum computing? I think the answer is that it has to do with quantum metrology. And it has very much to do that this was also the time when people for the first time, thought about building entangled atomic clocks, using entanglements to increase the precision in atomic clocks. And entanglement for quantum computers, this is also what we have to manipulate. And sort of historically, it went like this, that Ramsey invented this famous Ramsey interferometer, where you take atoms, individual atoms, and they're actually 2-level systems, spin up and spin down. Qubits, we would call them today. You put them into a superposition, you imprint phases, you take a very long time for these things to evolve, to imprint these phases, and then you see your interference fringes. And usually this is done with uncorrelated atoms leading in noise to what we call the standard quantum limit when you read out. This is the error that you make in the readout. So interferometers are limited by standard quantum limit in terms of noise, and we can visualize this as this blob on the Bloch sphere rotating around by this phase phi. And you can see if you have a finite number of atoms over here, this has a finite size that determines the resolution of your interferometer. And notice that where we are today is this, that Junier, for example, is building optical lattice clocks that have now 21 digits in terms of precision. And so if you ask an atomic physicist, what is a good qubit, we don't have to argue very much. Atomic clocks that have been developed, with an atomic clock transition that is very insensitive to external fields, is something that we have in our laboratory, and it's immediately an answer. We have stable qubits in a way which is just amazing. So for me, the discussion, let's make a good quantum memory, is something that should be seen relative to that. But as I said, this was also the time where Dave Wineland did ion trap experiment, that they had very few ions in the little traps. And so the discussion came up to improve the precision, in quantum metrology by adding squeezing to the whole story. Squeezing means that on your Bloch sphere, you no longer have the round coherent state we had before. We have now squeezing. You are trying to suppress the quantum noise in a certain direction here. Obviously, if you rotate something like that, you have a higher precision because it's actually sharp over here. This discussion of entangled states leading to noise properties beyond the standard quantum limit. And this was the time of spin squeezing, GHZ states, and all of that, so of entanglement. So they wanted to have entanglement, and the question was how. So the question of building a quantum computer came very much together with the question that the quantum metrology community was asking themselves. So if I go now back to the sort of historical developments of what the underlying features are of this trapped ion quantum computing or atomic clock, it was really that there was a long history. In the 1950s, people invented what we call the Paul trap, and what you learned at the end is that Dave Weinland, for example, was one of the first with Daymelt and so on to store single ions in a trap. Think of this like a harmonic oscillator. And also combined with the fact of laser cooling that allowed them to cool the single ion to the vibrational ground state. Of course, the idea was to keep these atoms around as long as possible to increase the interaction time. And so this led to these controlling single atoms on the level of single quanta. Here, for example, the motional degrees of freedom. But then came these discussions that at that point were sort of considered to be rather, I would say, foundations of quantum mechanics type of things about quantum mechanics. I sort of entered the whole business by, being interested in quantum noise. We discussed things like quantum jumps that were seen experimentally and by allowing the observation of single atoms continuously in this trapped situation that we had over here. Afterwards, of course, this became simply the readout for our quantum computer. So there were rather sort of a fundamental discussion in quantum mechanics, the development of quantum noise. All of these things came together and were sort of ready in the lab, and at the point where we started to think about, how can we build a quantum computer. So Ignacio Sirac was a postdoc at that point in my group in Boulder, and I just cite here from the basic paper and then sort of move on from there. If we had this little pictorial drawing of ions here in the trap with all of these internal clock degrees of freedom, we could address them with our lasers. And then we had, atomic structure like a ground and excited state, a very long-lived excited state over here. And then you could couple by turning on the laser to a strong optical transition where there would be a lot of fluorescence to do now quantum jumps and all of that. And what you want to do is qubits, gates, single qubit, two qubit, read out the decoherence. So let's see what we wrote at that point. I'm just quoting here from the text. In terms of qubits, I think I gave you the answers. We have atomic clock states. They live really very long. I mean, people have now this 10 to the minus 21 precision. That's just amazing. So I think we have an answer for qubits. There's no dispute about that. Single qubit was also sort of obvious, even technically not hard, because you have single ions with a distance of maybe 10 micrometer over here, and you can address with the laser to do your rotations, so the single qubit rotations. So that's pretty obvious, but in the lab it's not so easy to achieve. What we had to really add fundamentally new to the story was the two qubit state and about the two qubit entanglement. And our idea at that point was to use the quantized mode that I told you before. We can cool to the ground state, in order to have kind of a phonon bus, that was allowed us via laser manipulation and these phonons that are oscillating in a quantum state to entangle ions in a certain way. I'm not going to describe it. Then we had readout. Well, I just told you about quantum jumps. This is the theory of continuous measurement that provided us with this tool. And when it comes to decoherence, well, these people build atomic clocks, so that's a priori pretty good. This was the idea. And of course, today, from these early papers and these very, very early demonstrations by Dave Weinland, I just picked here from, say, Quantinum, an example from last year. And you should look at these numbers here. These are gate fidelities that this community achieves over here. This is a racetrack computer over here, not a string that we have been talking about over here, but of course now people can also do two-dimensional crystals. I think about Luming-1 has 1,000 ions, and they're trying to do these kind of things, hopefully with high fidelities also over there, sort of getting systems like that. I want to give particular credit, of course, to the early pioneer, Rainer Blatt, in Innsbruck, my collaborator, and many of these things, Chris Monroe and also Dave Weinland, that did these things. But I've stolen a slide here from Misha Lukin, sort of, where are we and what do we really want? So we have a lot of different platforms for doing these kind of things. But the ultimate quantum rivalry, if you want, is we would like to have controllability and also scalability. These are the two things that will be driving the evolution. And it is not obvious how to scale all of these systems up. And Misha Lukin just put this list down here. What's the current frontier? Task beyond classical computer, the quantum advantage discussion that we always have, and controlled with more than 1,000 qubits, testing and implementing useful algorithms and applications, error correction, and towards fault-tolerant quantum computing. This is sort of the checklist at that point for the future. And I want to say a few words also in this historical context about neutral atom quantum computing that we know now so well from these Rydberg arrays, where you have single atoms stored now in, for example, tweezers here, something developed by Philippe Grangier originally. What was added, the fact is that the deterministic loading, in the sense that you load them, they are randomly loaded, but then you're able to select the ones that are loaded and rearrange it, leading then to these Rydberg setups that we have right now, which I think is also one of the most promising ways of building a scalable quantum computer. So our contribution, and I'm going now back to 99, was when Misha Lukin was still a theorist at that point. We collaborated with him, was coming up with ideas how to entangle. And I had some background in Rydberg physics, and we wrote these 2 papers, fast quantum gates with neutral atoms, and then the dipole blockade mechanism. Together with Misha, we were working these things out, and we found they're working on the same sort of related things, so we put our work here together. And at the heart of all of these neutral atom setups is now something which is the dipole blockade mechanism, where if you, for example, have 2 atoms at a certain distance, when you excite them to high-lying Rydberg states, n being, I don't know, 50, 60, or even higher, and then these Rydberg orbits become as big as a little virus, for example, they have then huge interactions with each other. And you can use this huge interaction. If I have 2 atoms that I would like to excite to the Rydberg state, if I excite one and then I would like to excite the second one, because of the very strong interaction, this line will be shifted, like in quantum dots where we have a Coulomb blockade. And so you can only excite one atom or the other atom, but not both at the same time. And this was sort of a mechanism that also avoided, if I excite 2 atoms up here, they will see a huge force and they will fly apart. So there would be, entanglement kind of coupled, and there would be a form of motional decoherence. This could all be avoided over here, and it was a fast gate. And similar over here, Misha Lukin was thinking more about atomic ensemble. So this was the basis. And today, when I see like from Jeff Thompson, gate fidelities that have 99.9 over here, that's pretty good, and of course the early experiments from these 2 gentlemen over here. So that's where we are today, and the futures, of course, when I go to Harvard, as one example, is this, atom arrays where you can move atoms around in these tweezers. You can do these kind of gates that we discussed over here. And there's this paper now written to this fault-tolerant quantum computing. And I think the amazing thing is here, this is really a scalable system, up to a certain point, of course. And this may be a way, of addressing, many of these things that we've been dreaming of for quite a long time. I should say here that I was hoping that Misha Lukin would be here to give a talk. This was the plan originally, and he would sort of pick up from over here. But we can maybe discuss afterwards, more details about that. Something very quick about what I don't really want to talk about much is with quantum networks. You build quantum computers and you would like to connect them like the cores on the chip or like a local area network. You need, a little quantum computer, which in the case of atoms would be what I just talked about before. But we also have optical light interfaces where you can convert stationary to flying qubits here and connect them via channels. And there's all of these hardware and protocols behind that, how to do all of that. We wrote papers together with Jeff Kimball, who sadly passed away now last year, on all of these kind of things here, and he wrote this beautiful article about the quantum internet. I just want to say as sort of a technological highlight here, we came up with things like the quantum repeater protocol that allows you to distill, long distance EPR pairs that you might need for teleportation. And when you go to China and you see that in, for example, Shanghai, they have now a network which is based on these kind of protocols, which is a quantum repeater network, sort of for long-distance quantum communication. That's pretty fascinating. So this is something that exists in the lab now on the rather mature level and is sort of ready to be used, I guess, out there. When in quantum computing, of course, we still have to wait a little bit. But let me now go to what has been really my hobby for all of these years, which is quantum simulation, that I see as one of the most promising applications, of all of these quantum information things that we do, having to do with solving a quantum many-body problem. And there's a lot of problems out there. So this is bringing quantum computers or special purpose quantum computers that we call quantum simulators back to physics by trying to solve problems that they should solve ideally, namely quantum mechanical problem. And sort of to illustrate what we mean by that, suppose that you have some quantum material or whatever. At the end, what we write down is a Hamiltonian, a many-body Hamiltonian. And of course, this is now condensed matter physics. You can try to solve it classically, of course, what we always do traditionally. There's all of these fantastic algorithms, Monte Carlo, tensor networks or whatever. But here, of course, we put these things on some quantum machine, either quantum computer, in the form as before, it's digital. You heard in the Google talk the other day about the digital version of all of that. You can do it analog, where you have these Hamiltonians find a native, immediate implementation on these systems here, or do some sort of a hybrid, which is what we normally do. The hope is, of course, to get what, under quote here, to get this quantum advantage. And from an atomic physics point of view, of course, an entry point to this whole topic was, again, originally motivated by metrology, but it took on its own life, was the fact that these gentlemen over here were able to create both Einstein condensates, essentially zero temperature, quantum degenerate gases in the lab, first for bosons, then also for fermions. And but they were weakly interacting. And the question is always, when you have something like that, can we use it in our context? And very early on in these days, we were thinking about, well, can we get rid of this weakly interacting? Because condensed matter people seem to be not very interested in weakly interacting. Bogolyubov know how to solve these problems. Can we make it strongly interacting? And our answer was, on the theory side, to put this into optical lattices. Basically, if you load the BC in the first band over here, in an optical lattice, which is created by laser light. It's an array of little microtraps, and these atoms can now tunnel around and hop around. You can see that by making this barrier higher and higher and higher, they tunnel slower and slower, so there's a way of tuning the effective mass, and we can then tune a system from weakly interacting to strongly interacting, from across a quantum phase transition. And of course, Tobias Sachdev book and all of these things was sort of, it's really the theoretical underpinning of all of that. So this was the idea of creating Bose-Hubbard models, and of course, in Munich, by these three gentlemen over here, then this first experiment was done along these lines, and I really claim it was the first analog quantum simulation experiment that, of course, led to many things. We have now fermions, and see the talk by Manuel Bloch over here. So again, I want to stop over here and move on to work that I've been doing in Innsbruck now during the last maybe 5 or 6 years that I would like to summarize here briefly, at least in spirit, which is on programmable analog quantum simulators. And Emmanuel and myself are in European programs and have been studying these things, and I find that we coming with different platforms together as a mixture of theorists and experimentalists are doing quite exciting things. And the story I would like to pick out here today is this, that in Innsbruck we have downstairs in the lab of Rainer Blatt, a linear ion trap. In some context, we were even able to sort of access it from our desks, having an access to a quantum machine, like quantum computing or quantum simulation on a kind of an internal quantum internet. And the story I would like to tell you is the story that Subi had talked about from his point of view, condensed matter physics on Tuesday. He spoke a lot about entanglement, and I will ask questions: how do we measure this entanglement? And can we do experiment where we make this entanglement from entanglement entropy spectrum or even an entanglement Hamiltonian tomography visible in the lab, by adding now protocols that we have to run. So we have to invent now quantum optical protocols to do that. And the example I'm going to discuss here will be the randomized measurement toolbox. And John Breskill called these things classical shadows. We came from two different sides, but that's really very much related over here. And I will say a few words about variational quantum simulation that becomes a useful tool for doing that. I would say that what this shows, and also the example down here, where we collaborated with Quera on lattice gauge theories in a recent paper, many of these experiments are now developed at a very, very high level. And, like Quera, company at Harvard, trying to sell, Rydberg simulators over here, that they're also becoming useful in the sense that you can really study highly non-trivial things by taking these existing setups. We had the luck of being able to collaborate with these experimentalists here very closely to do some of these things. But this experiment was run in an Aquila 256 qubit machine running in a 2D analog quantum simulation mode over here. And I will have just like, I thought that Misha Lukin might talk about this second part over here, just added a few slides on that. Okay, so what's the problem that we want to do? If you go to the lab, well, people have these ion traps. They have Hamiltonians, like the one which is down here. So this ion trap, if you don't do quantum computing but shine in lasers continuously, basically realize, in terms of the different spin that are realized by these ions over here, kind of a transverse Ising model that has the feature of having long-range interactions over here. So this is a power law, JRJ, which makes the model more interesting in the sense of being non-integrable over here. And if you go to the lab, the sort of obvious immediate experiments that you might do is this: well, let's prepare product states, spin up, spin down, and why not simply apply the time evolution from this thing over here, studying quench dynamics, getting an entangled state out. Notice that, well, it's a quantum many-body system which is controlled in the sense that we have this Hamiltonian over here, isolated quantum systems, and there will be entanglement in the time evolution. What about thermalization? So there's immediately a range of topics coming up. And the way how experimentalists read out and sort of doing measurement is they make projective, single spin measurements over here by quantum jumps. I mentioned this earlier, measuring these individual qubits over here. We have projective measurements. You take statistics and then get distribution out for particular bit strings. This is how these experiments are done. So the interesting part, as I said, is, of course, that there's entanglement generation in these quench dynamics when you go on over here. So let's think a little bit about it, what it means, and can we see that and sort of classify it. When the theorist thinks about entanglement, like in the form of this bipartite entanglement, I'm drawing here a 2D lattice, so the experiment was 1D, even though all of these things that I tell you in the following work immediately on different platforms, 2D or whatever. So imagine that you have a quantum system, you have your quench dynamics, so you prepare the ground state. Let's bipartition, these lattices over here into A and also B. So in our sketch over here would be that we take a subsystem out of the qubits that we have over here. And one question that you might ask is this, and this is sort of the most basic form of entanglement. If I have a pure state over here while I do my quench, I can always do a Schmidt decomposition. And you can see the Schmidt decomposition is this bipartition into A and B states, and there will be a superposition up to a certain chi. This is kind of a measure of entanglement. And these coefficients that go in front here, which is basically the eigenvalues, so the entanglement spectrum of this entanglement Hamiltonian, which is the reduced density matrix that we prepare over here. If we just look at this subsystem, these are the Schmidt coefficients, and this evolution from a product state over here initially to something which is entangled will, of course, then be visualized by the fact that we would like to see, for example, the build-up here of these different Schmidt coefficients live, how we do our quench dynamics. Can we measure that? And this is where people like myself now come in, where we are trying to develop protocols where on these machines that we sort of invented to some extent, 30 years ago, and how they come back to us, and we can try to see some of these effects, like this very fundamental, can we see the Schmidt decomposition? And the question is, of course, how to measure all of that, and I will say a few words about this afterwards, in terms of this randomized measurement toolbox as one example of doing that. Let me just show you the results from that. So if I take here on purpose a very small 10 ion chain, you can do that immediately now for 50 if you want to, and I plot now here the Schmidt coefficients. We have here our superposition, and it's just plotting the first coefficient here. You can see at the very beginning, as a function of time, quench time over here, you prepare the product state. So this is now theory. So there's products. So one is 1 and the other ones are 0, and you can see this thing decaying, and this is the buildup of entanglement over here. When you now do an experiment, you can see now the experimental data here that lie very much on this curve. This is entanglement. This is measuring the entanglement spectrum, the Schmidt decomposition live during a quench, where we can really see in detail all of that. I would be very interested to do that, like measuring a Marchenko-Pastur distribution of all of that. Then you really have to scale it up to very large system sizes. And as just additional bonus, I want to say here that this protocol that I will talk about a little bit later on also gives you the von Neumann entropy. You can see here the growth of the von Neumann entanglement entropy in time. This is the theory down here. This is sort of the error-corrected version of this thing here. These things kind of agree. So this should be a teaser for you why we do that. But you should also notice that we just take this bare bone simulator. We can also run very simple algorithms on that. For example, what we can do is this, that I got my spins over here, I prepare them in a product state, and I apply now this Ising Hamiltonian down here that is built in natively, and this works for 51 qubits, with perfectly, I would say. Look at this thing like being a 51 qubit gate that acts on all of these atoms. This is something that almost comes for free in the systems, but we also have in the simulators is the single site addressing, so we can build up circuits by playing here with parameters to realize different gate sets over here, and then building up a certain family of states over here that depend on these parameters that we choose. You can just cook up a circuit up to a certain depth. Decoherence is about maybe 1% in the system, so it's actually pretty small. Creating families of entangled state that are parameterized in a certain way, and I guess the building blocks are the one of this entangling, many qubit entangling, together with these local rotations, and this leads immediately, of course, to the variational quantum algorithms that chemists have discussed that we can implement here ideally, but maybe more in a many-body or condensed matter context. For example, if I give you a target Hamiltonian, which has nothing to do with the one that produced the gate over here. So this target Hamiltonian you can write down, and we'll do that now for a spin model, for example, which is a Heisenberg model. You can ask yourself, among this family of variational states that you created over here, when we minimize this landscape of these parameters over here and find a minimum, this is what the variational quantum eigensolver does. We find then in the lab, approximate ground states of the Hamiltonian that you have over here. I show you one example, and the reason for showing you the example is that I will need this a little bit later when we talk about entanglement, and this will be one of the results that we need there. Suppose that you decide one day that you take as a target model, a Heisenberg model, anisotropic, that has this phase diagram down here, critical regime over here, then there's a gapped phase over here. And suppose that we can implement it. Well, a native ion simulator does not implement this thing, but what we can try to do is to produce the ground state of a Hamiltonian sort of with our quantum simulator, which is the transverse field Ising model in the sense of cooking up a certain sequence of gates, not going to tell you what. Let me just show you what the results are. If you run this optimization algorithm, and we have developed a lot of tools behind that, then you can cool down eventually and prepare a quantum state in the lab, which is an approximate ground state of this Hamiltonian. If I take 51 ions, this is a pretty large Hilbert space, we go down to that, we can compare this with DMRG calculations. This state that we generate over here in the lab corresponds to about a superposition of 300 of the lowest states, while the total Hilbert space is, of course, 2 to the 51, much larger. So you're cooling down to temperatures that are in this sense percent limit, but notice that, of course, this Hamiltonian is never physically realized in the lab. We have just downgraded our quantum simulator as a variational device to produce approximate ground states of this thing over here. So at that point, let me say a few words about these randomized measurements that we developed, with these students and then the postdocs, sorry, over here. And this was then related to the classical shadows that John Breskel discussed. We wrote this thing up together in a review. You can read this. This came out in Nature Physics now a few years ago that has all of the relevant references here. So what do we do? What we can easily do in these experiments is something like this. Suppose that you take again your quench dynamics. You can do some post-processing, quantum post-processing, again, making use of this, kind of a gate set that I described, of this n-body gate that we have, single particle gate that comes for free in these machines. And one thing that we would like to do is, for example, to do random unitary that we want to apply to this thing over here. You might say, why would I scramble up this beautiful wave function that I have over here? Well, the kind of things that you can do over here, and think of this as either being a global random unitary from the COE, or local random unitaries that are just applied here locally to all of that. We'll see this also on the next slide. Producing again our distributions now of the bit strings, depending on the U that you have over here. And so this becomes then a random variable, these probabilities depending on U. And the kind of things that you can do, and I'm just doing here the most simple example, is that you can look at these classical cross correlations between these probabilities. So these are quantum probabilities over here, but this is a classical average at the end over this unitary COE. And this has the properties of a 2 design. So this allows us then to extract, from these kind of averages that we do over here, interesting quantities like the Rayleigh entropy, as you will see on the next slide. Experimentalists really love it because they can really run this system, maybe one time in lab number 1 and second in lab number 2, and then put all of these data together and so on. So That's a tool that experimentalists love. Let me just mention that what you can do easily is, of course, single-site random rotations over here. When it becomes global, it's much more difficult. There have been ideas, but then you need quantum computing circuits and so on to produce that, to produce it also globally. But the system also provides an sort of an easy, cheap way of even producing, global random unitaries. If I, take a sequence of these Hamiltonians and I pick random parameters in this Hamiltonian just from the transverse Ising model that we had natively in the lab, then this can also approximate very well random unitaries just being chaotic dynamics, like chaotic Floquet dynamics. So this becomes a way of sort of realizing this thing in a different way. But what's really the most simple case is the one where you take local random unitaries over here, then you can write out, these unitaries now as product of the individual unitaries. So these are single qubit unitaries, very easy to implement in the lab. You just take your Bloch sphere, spin 1/2. You can rotate them randomly wherever you would like to have. Then you can derive, for example, formulas when these are the probabilities, the subsystem over here for these random unitaries, and you cross-correlate them according to a certain formula. You can see that things come out that are interesting, like this Rayleigh entropy over here, which is the purity, of the state over here as one measure of entanglement. And we can extend these ideas then even to entanglement Hamiltonian tomography. And I will not tell you, there's a lot of technical details, how they derived it and how to think about it, how does it scale with the number of measurements and so on. But I will skip this in my talk and simply say that we've used this toolbox, in a whole range of different systems. There was a lot of discussion of out-of-time ordered correlation functions. We wrote a theory paper based on randomized measurement. The experimentalists started in the lab. Topological invariant, this is still waiting. Here, we can measure topological invariance in topology using these tools. Partially transposed density matrix. This was a paper together also with Caltech, John Breskill. Again, there's been experimental data for that. Here's the topic of entanglement Hamiltonian tomography. I'll say a few words about this. In relation to the talk on Monday, Michael Berry talked about quantum chaos and his spectral form factor came in. I think he called it pair correlation function. We know how to measure these things in many body systems, and this allows us to see, for example, this chaotic ramp, and then they go over to the at the Heisenberg time to the flat behavior. Provides tool for seeing this, or what's sort of entertaining, and maybe I should start with that, the quantum member effect. Let me start with the lowest one because that's kind of entertaining and interesting story by itself. So what is quantum member effect? This is a paper that came out now 1 year ago. This was work done by Manoj. She's the experimentalist in the lab in Innsbruck. And our main contact, and Lata, his wife, is a theorist. She worked in our group. So here's theory and experiments sort of in one family. And the particular idea where we applied this random measurement came from Calabrese, in the theory paper that they wrote just a little before. They came to us, do you know how to measure? And of course, we said yes. So the effect is quite entertaining. Maybe some of you have heard about the classical member effect, where a young schoolboy found out by doing experiments, I think highly relevant experiments, by mixing ice cream, and then you put them in the freezer to freeze them down. If you put in with a higher temperature initially, they freeze faster. Okay. I think that's a very important, and relevant, observation, because it means that you can get the ice cream faster. And the question was, is there a similar effect? There's been a lot of discussion about these things classically, of course, and this effect has been seen very often. So this has to do with if you're very far off from equilibrium, then you might relax sort of faster. So Pascal came up with an idea how to find a quantum version of all of that. And basically, we go back to our setup over here. And you should note that the Hamiltonian over here, for example, can be an XY model, which is rotationally invariant around the z-axis. But if I take an initial condition over here, where my spin is not along the z-axis, my initial condition, but I tilt it by a certain amount, you might interpret this as a broken symmetry, initial condition relative to this symmetry that you have in the Hamiltonian over here. So if you look at the reduced density here, operator here as a function of time, you can see that initially, it may be sort of, it will be the different charge sectors, corresponding to this conservation law that we have over here. You're preparing off-diagonal element, and what the quench basically does, that you relax to an equilibrium distribution where you kill all of these off-diagonal elements. And again, you can define, a measure of this distance between these two states here as what they called entanglement asymmetry. It's like, again, our Rayleigh entropies that we had now mentioned it before. Well, you can go to the lab and try to see that, so if you tilt the angle more, so more symmetry broken, you relax faster, okay, and here. So I think it's quite a curious observation. I'm never sure how deep the meaning of these member things and so on are, but these, they are highly entertaining, and sort of I would like to know myself a little bit more, that I can look at the system and see that, this relaxes faster, not based on certain criteria, but this finding out sort of a discussion can be done in integrable systems where you have quasi-particles and they give you a picture of what's going on, but sort of this is a non-integrable system, which made it interesting by itself. Okay. I showed you before that we can prepare for a Heisenberg model, with our few gates, something like an approximate ground state. Okay, I'm going to change now the story and tell you a little bit about entanglement spectroscopy, where we're using this ability to investigate now in the lab, for example, things that have to do with very interesting properties of excited and ground states, of seeing the difference in entanglement structure that we see in many body systems. So take the following discussion as an example, that we could do over here, but the whole story is much more general. It applies to 1D, 2D, and so on, and across all different platforms. And I think also the tool set, how we do that, is much more generalizable. But of course, we had these experiments and the possibilities in our hands. So let me discuss it here with that. Again, let's take an abstract sense, a many-body problem, which is somehow k-local over here, and I'm drawing here an energy spectrum, and I'll be interested in bipartite entanglement as indicated over here. And to be more specific, let's think about the Heisenberg model, where we just prepared an approximate ground state, gapless over here, and then the gapped phase over here. And we can prepare for all of these different parameters with our quantum machine, approximate ground states. So we can not only prepare ground states, but we can also prepare excited states. I mean, we are drawing here single levels, but in reality, of course, this will be a bunch of levels at a few hundred in our case, in reality. Effective temperature being extremely low, of course, and similar for the excited state, which is over here. But suppose that we can do that, what kind of physics can we now ask or sort of understand in terms of this entanglement? The first thing that you might say is this, that, if you look at the ground state of this system, it should have area law entanglement, which in the case over here, this is like a conformal field theory at the critical point, for example. You might have a central charge equal to 1 over here. There will be a log correction. We didn't see that there. Well, we saw it, but we weren't entirely sure in the experiment at the end. But there will be area law over here, and if you go to the excited state, there will be volume law. And we wanted to see that, but we wanted to see that even more, as you will see now in a minute. What we also wanted to see is something on the structure of the Gibbs state. Here is the ion chain down here. You take the sub-region out over here. At the end, this could be even up to 20 ions or something like this. We would like to make some statements about that reduced density operator of the system over here. And if I take an excited state and I trace out, these regions over here, all of you would immediately agree, well, it will be something like a Gibbs state, and according to the eigenstate thermalization hypothesis, this is what you would sort of expect. And so there will be a state with a constant temperature, so if you allow me to plot over here for different system sizes, if I visualize this Gibbs state over here, it would be something like a flat local temperature, and you can see if I make it large at the same temperature, and of course this being a thermal state over here, volume law will be proportional to 1D system like the LA that we have over here. So what happens now if you cool under quote here to the ground state? Well, then the story becomes really interesting because, in the mathematical literature in 75 or so, Bisuniano and Wichmann discussed in the context of quantum field theories, relativistic quantum field theories, the ground state, and this was then generalized by Cassini-Wert and Myers, more recently to the case of conformal field theory, like what applies over here. And I'm using now their prediction, for the entanglement structure of the ground state, the reduced density matrix, and what the corresponding entanglement Hamiltonian is translated now to a many-body system as a conjecture, you might say it over here, but it's a guideline what we would expect. And if you read these papers, you find that the reduced density operator again has the form of a Gibbs state. This was the Hamiltonian here, the B is here again, but with a local temperature, and this local temperature means that this beta, inverse temperature, has the form of a parabola over here. You can plot these parabolas, for different system sizes over here. And this is sort of the indication that, that if I go very close to the cut over here, the effective local temperature is very high, meaning that there's entanglement across the cut. If I move away, it sort of gets down. So these are fundamental predictions just coming from conformal field theory, and this implies then, of course, also this area law here at the end. And if you go to the lab and, with these randomized measurements, I'm not telling you the details now here. Yes, indeed, you see, if I go to the ground state and I measure now here the von Neumann entropy that we can, based on our techniques, we see area law for the excited state, thermal state over here. It's not a single eigenstate we prepare, we see volume law. For the excited state, you can see here this effective local temperature that we plot over here would be basically flat. It's not completely flat because we were not able to prepare really a thermal state, but it is much more flat than the other one, which has a nice form of a parabola here. If you go away from the regime where CFT applies to the gap regime, you can see sort of a similar behavior over here. Agrees pretty well with DMRG calculations, but there was some little bit of deviations up here. So if I show you what this parabola really looks like, this is this Cassini-Werner-Myers parabola. They got the Dirac medal actually, last year from the ICDP for also this kind of a work. And of course, we see a counterpart in the many-body system in our experiments, where we can see these different parabolas over here matching theory extremely well. And notice that we can do that up to 20 lattice size. So that's actually quite amazing. You can see this is sort of an interesting door opener for topics. Here, like we can prepare approximate states of a conformal field theory. We can measure entanglement. And if you heard the talk yesterday, maybe Kevin can do some sort of, under quote, gravity experiments here with his tool set in the lab. Okay, this is something to be discussed beyond my expertise. I want to add here just very briefly a few more statements about this programmable simulator story. And emphasize also quantum sensors. We got here a controlled many-body system that allows us to play all of these entanglement tricks. What about quantum sensors and metrology? And I want to point out that with Junier, I wrote an article in Physical Review Letters. They allow now these essays, and we wrote about the future of quantum sensing and that entanglement is very important. It came up with the different platforms from quantum sensing networks, atomic clocks and investigating gravity. And here's this usual kind of list that one says over here. The question is simply, can we use these abilities that we can manipulate, create entanglement with our machines, also in this context of quantum sensing? And I just want to give you a very simple example that we did, again, on the same tool set. And I'm back now here to my RAMS interferometer. That we said before, it's just that I take a bunch of atoms, pi/2 pulses, I imprint a phase, close the interferometer, measure my interference fringes. This is for uncorrelated atoms. But imagine now that if we put our ability to put here a variational gate set in here, that is generated on a very large scale, for example, with our Hamiltonians that we have in the lab, like the transverse Ising models, but we can put them together, in a certain way. To make variational circuits that will produce any input state within the variational class, and do the same also for the output. So we have here correlated measurement, and then optimize these variational parameters here, well, to do what? For example, the noise that we get in this interferometer, and tailor the noise properties. So find an optimal RAMS interferometer, putting in all sorts of different entanglement and play with that, and let the machine find out itself what's sort of the best way of doing it. So in this sense, the idea is now that we no longer have energy as a cost function, but some metrological cost function like signal-to-noise ratio, or like in an atomic clock, you would say, well, I would like to have a little noise of a very broad range of these phases over here, and then you run variational algorithms on your quantum machine, on your quantum simulator, whatever it is, in order to find the optimal operating point so that you get the lowest noise and the noise properties that you want to have for your interferometer, approaching very often, the limit of the optimal RAMS interferometer. This is the one by using all possible entanglements for the RAMS interferometry. You might say that you know the answer, it's GHG states, but it's not the question that we want to ask now here. When we do this feedback, we are asking a question relevant for atomic clocks. If I run a standard interferometer, you can see up here the beautiful interference fringes, and you can see down here what the noise properties are as a function of a phase. We would like to have this noise as low as possible go down here, And now we are putting a constraint in our cost function, find those entangling states and measurement correlated that make this noise as deep as possible, but also as broad as possible over here, this dynamic range that we have. And then we go to the quantum machine and we first put something in front and ask, what would you like to do with that? What's the optimal parameter? If you ask you reduce the noise, we can see the noise goes down here. This is basically squeezing. If I add some variational circuits only at the end, it gives me the possibility, by optimizing the cost function, something which is very broad. So the noise is about the same, but it's very broad. There's a much broader dynamic range. And if you combine these two things here together, you get the red curve over here, which is much broader, so it's low as well as broad. That's exactly what these people want when they design interferometers in terms of these noise properties. And you also can see that it comes with the fact that the dynamic range of the interferometer has increased here significantly. These tools are available. You can see now the story. We started with atomic clocks, and then we went over now to quantum computers, but these quantum computer ideas are now coming back to improve now also quantum sensors. So I think I don't have so much. Okay, 2 minutes. I want to say a few more things. So I was hoping that Misha Lukin would talk about this over here. So for the last 2.5 years, we had a collaboration with Misha Lukin and then Quera, the Quera team, the company that came out of Harvard that builds on a professional level, this Aquila device, 256 qubits, also available on the internet. And we came up with ideas how to do string breaking. Okay, so to make this very short, I apologize. Subir talked a lot about lattice gauge theories in his talk, and we are basically taking their work and their ideas, but we are adding here one feature, and this was seen in this experiment. We would like to add here a story where we add classical charges that in the Rydberg 2D array then would be defects that we have in there. And seeing strings, this is like when you do quantum chromodynamics and you have your quarks and there is the string connecting these two, and if you make it larger and larger, eventually a string will break, creating particle pairs, and then you get mesons. We would like to see a string breaking in these simulators over here. Sort of like here is the string breaking, you make the string longer and longer, but at one point the string sort of breaks, and to see this phenomenon. This was done at Quera. Different string configurations, and we could sort of map the 2D array. Here's the mass, here's the string tension. I'm very short over here, broken string phase, and then the string parameter over here, theory calculations, and then at the end there was an experiment that allowed us to see that. So Pedram gave a very nice talk where they did a digital simulation. This is now really the difference here that we have an analog device. So this is really quantum matter sitting in the lab, having these properties that really sort of displays these kind of things and can be the playground for that. And we not only did it here for the ground state, you can also do it dynamically that if you start with a certain configuration and you quench, that you see that the string breaking dynamics going on over here, okay? I want to conclude here, maybe 1 more minute, okay, thank you, okay. About statements which are more like an outlook here, sort of in search for relevant applications. I think it's very important in our business over here to find relevant applications, I want to say a few words about something that we've been thinking about for a while. I just want to get across the basic idea very qualitatively now. Then topics like, characterization, verification. What you really would like to do is bounded error quantum simulation. I know the Hamiltonian has been in the lab implemented according to this Hamiltonian learning. Can I make statements, about bounded errors from a theoretical point of view by sort of analyzing, based on Hamiltonian learning, the properties that I learned the Hamiltonian with a certain parameter range. So this would make these devices quantitative devices for predictions. This is really what we want. And then there would be some ideas about novel quantum algorithms that I probably don't have time. Let me just get across here the basic idea, and this will really only take 1 minute, sorry. So experiments are normally done like, I got an input Hamiltonian over here, and I've taken an example that, of course, Emmanuel will talk about much later on, Fermi-Hubbard experiment, but this can be phrased in any other device also. Suppose that you write down a Hamiltonian, like on the square lattice, and you ask the question, can I see superconductivity over here, D-wave? Flatiron, of course, knows the answers to some of these things, but suppose that you don't. So you have an input Hamiltonian, you do an experiment over here, and your hope is, well, theory predicts maybe some phase diagram, okay, over here. Maybe your favorite theorist did here, I don't know, mean field theory, and he came up, convinced you, oh, you should try to do this experiment, and will be highly visible, of course. And let's call it an experiment in our fictitious stories in search for high DC. Then you do the experiment, and well, okay, you didn't see very much, so what's the point? Maybe at this point, an experimentalist might go back and say, let me see if I did something wrong. And this is now this verification step that we have. You know, when you have an Hamiltonian, did you think that you implement it? Of course, experimentalists are master in finding out what these parameters are, but there may be additional terms over here, you know, that they don't look for because they don't think about them. We can do something like Hamiltonian learning by using, for example, a quantum gas microscope. You might analyze what was, based on measurement, really the structure, the operator structure of the Hamiltonian implemented over here. So can we learn this operator structure, compare it with the one that we wanted to have, and then sort of see to what extent they differ? But we can also turn now, and this is the message really on this side, our whole quantum simulation story around. Normally we go from here, you know, over here, but suppose that you as a theorist draw an interesting phase diagram and you identify a certain parameter feature that you would like to amplify. Maybe we should use our quantum machine to learn really what the Hamiltonian is that generates these features in the first place. So in this sense, this is what we call quantum material design. It would sort of, from the properties, you know, design now, point out the Hamiltonian, doing in between some simulations, maybe beyond classical computing, optimizing cost function that have these features that you wanted to have, finding out a corresponding learned Hamiltonian over here. And you want to do that iteratively. So we have done this, implemented for a first step where we took, just this a ladder over here, Christian Cockale was who did that. And then ask, I would like to have D-wave, what do I have to add to the Hamiltonian over here? Or should I learn the Hamiltonian back, the feature? And the answer was something that, of course, flat iron knows, and it's not really visible over here. Basically, this protocol told us, you can see these crosses, add this axis over here in terms of tunneling, cross tunneling to the story, then you get more features. So this allows us sort of to find, based on properties that you specify, then interesting properties there, and it also leads to this bounded error simulation, but I think that my chairman is getting nervous, so it's maybe time to stop here. Let me just say that I gave you a little tour, that started from early history. And I think it's quite amazing that these quantum machines that we sort of dreamed up originally, credit should go to my experimental colleagues for developing them over all these years, but now they're coming back to us as something that we as theorists can play with. And while in the early days, we were always writing our theory papers and hoping that an experimentalist might pick up these ideas and then do it later. Very often we can just go now to the lab and check it immediately. And I think that this is exciting times. Thank you.
Thank you. I'm sure all of you will agree that it's exciting times as well. So let's thank Peter again. And we'll take a few questions. We have time probably for 3 questions. Yes.
Exceptional work, obviously. So I have a question about your discovery of Hamiltonian, the thing that you just covered.
This thing here.
Yeah.
Okay.
So
I didn't really talk about it. No,
yeah.
Just telling you here are ideas.
Correct.
Life will not finish.
So I just want to know. So if you have, isn't it a one-to-many problem? I mean, in the sense of, could you not visualize that the end state that you want to actually, reconstruct a possible Hamiltonian from is actually a possible manifestation of many Hamiltonians that you could write?
Okay, so what you're saying, is this thing unique? Yeah. This is what you're saying?
Yes.
And I say, it is not unique, but this is a feature, okay? It is a feature in the following sense that if I give you certain properties, like, I put here as under quote D-wave as a fancy example, if there's several Hamiltonians that realize this feature that I want, I'm very happy because then I go to my chemist friend and tell them, here's a list of Hamiltonians. Can you realize one of them, maybe with your quantum material, maybe one is easier than the other one. And so in this sense, what you point out is true, but it is for us a feature because it broadens the applicability of the idea.
Okay, thanks.
Yes.
Hi, here. This is a question regarding what you said about the fast cooling. So when you translated it into the quantum system,
Okay. This
Yeah,
story
so
about the
I'm
quantum
curious.
member effect. Yeah.
Yeah,
I
so
find this more entertaining, I have to say, than it is deep. Okay.
yeah,
Go ahead.
yeah, I'm trying to just understand. So is there a possibility of defining a distance? See, there are different distance measure. So imagine that you have an equilibrium state and there are different non-equilibrium configurations or states. And
Yeah.
you define an appropriate distance measure whose optimization will give you the fastest cooling. Is it possible or it's a hard problem?
Yes, as a matter of fact, in this paper, I didn't really have time to talk about it. Different distance measures were used, and so to see the dependence, all of that. For me personally, I have to say that, I see this as an entertaining and qualitative story. So, if you use different distance measures, you will also see that, and we tried it out with different one, but maybe you have your favorite one, and we should try out that one. The question with this member effect is first of all, we would like to find that we can engineer a member effect. If I have some device and I can cool it down faster, this could be technologically quite interesting. It's very difficult to identify really, what is the feature that makes it now relax faster, because this is relaxation very far from equilibrium. And so to develop an intuition, what really is, I found it very difficult to do that. And this is sort of a question I have in this context. And the other part is, of course, that, I think it is an interesting, entertaining, qualitative feature, and we should leave it at that level. Okay.
Thank you.
Yeah, we'll take the last question.
So I have a question regarding what is the state of the art in our theoretical...
So can I just ask who's talking? Okay,
Yeah.
sorry. Okay.
Sorry. What is the state of the art in our theoretical understanding and experimental probing of dynamics across phase transitions? So physics beyond Kibble-Zurich mechanism.
Okay, well, you're asking me about now the experimental... you ask about protocols to investigate these things, or you
Yes.
have a...
Experimental protocols.
Okay, so
and
you
what
have a
is
second order phase transition, and you would like to investigate...
the dynamics across the phase transition.
So then I would simply ask you, what features are you interested in? Give me a theoretical quantity that you would like to measure, and we can maybe, hopefully, cook up a protocol along these lines. There were these Kibble-Zurich experiments. We did some theory. So with Wojciech Surek, we wrote a theory paper on Kibble-Zurich, and then Misha Lukin came along and did an experiment, in the Rydberg simulator, quenching across that, and then seeing Kibble-Zurich kind of physics. What would you like to see across above that?
Spectral function.
Spectral functions. I think we should talk about it. I've immediately some ideas, and there are other theorists also had ideas. If you give us interesting questions, we are the ones that hopefully can translate these things from a protocol, invent a protocol that would measure that. So I would be quite optimistic, but we have to talk about details here.
Okay, since we are running a little behind schedule, we'll have to close this session. Please join me in thanking Professor Zoller again for a wonderful talk. Thank you so much.